Hi all. So this is the last theorem about the integral calculus. Okay, so I am just giving the theorem first. So if you integrate the curl of a vector field over a surface, that is exactly equal to the line integral of the vector field over the loop which encloses the surface. So what is the meaning of it? So that means if we have some surface of some arbitrary shape, and what I am going to do is I am going to find the surface integral of the curl of the vector field. So surface integral means I can split this entire surface into small segments. So I'm going to add del cross V over all these small infinitesimal areas. Now this sum, this integration, the surface integration is exactly equal to the integral of V dot dl over this loop, the loop which encloses the surface, the closed loop which encloses surface. Okay, so this line, or we can call it the closed loop, that is the, I think that would be the better word. Closed loop encloses surface. So this is called the fundamental theorem of curl, and some textbook also called it as Stokes theorem. So again, no proof is required for this theorem as well. Okay, but we can get one information from this theorem. So we know that in case of conservative vector field, a closed integral v dot dl is 0. Okay, so if we have some conservative vector field v, then closed integral v dot dl is 0. Now according to Stokes theorem, using Stokes theorem, the closed integral v dot dl is equal to integral del cross v dot ds, isn't it? If closed integral v dot dl is 0, then the surface integral of del cross v should also be 0. But the area integral cannot be 0. So this implies that del cross v must be 0. So this is another condition, the another criteria to check whether your vector field is conservative or not. So if your vector field is conservative, so if the vector field v is conservative, then the its curl is 0. So if the vector field v is conservative, then its curl is 0. This we can use as the checking stone, the checking criteria for the conservative nature of the vector field. Okay, so now finally we can discuss the qualitatively how the Stokes theorem happens. Okay, so if you look at the curl, so the curl actually gives the curveness of the vector field. So if you calculate del cross v, so del cross v gives the curly nature of the vector field. Okay, so if you add this del cross v over the all area, what would happen is the at the interior, the del cross v, they cancels each other. Okay, so finally what will remain is we'll get the integral v only over the loop, only over the loop which encloses the surface. So if you look at the curly nature of v here, so it is the, if curls, it would be like this, and for the next segment it would be like this. Now this would cancel. So this v cancels. Okay, so finally we'll have the integral over v only over the boundary. So that is what we have written here, because this closed loop is basically the boundary of the surface. Okay, so if the surface itself is closed, then what would happen? If the surface is closed, then there is no loop which encloses the boundary, which encloses the surface. So that means if you are integrating del cross v over a closed surface, it is always zero. So this is the corollary statement of Stokes theorem. Okay, so that's all about the fundamental theorems of the integration or integral calculus, the gradient, divergence, and the curl. Okay, so next we have to define two more things. That is what is called the curl-less vector field and divergence-less vector field. So we have already said what is meant by curl-less vector field. So curl-less vector field is also called conservative vector field. So curl-less means del cross v equal to 0. So del cross v equal to 0 implies the closed integral v dot dl equal to 0. So that means v is conservative or v is curl-less. And what is divergence-less vector field? So divergence-less vector field. So if any vector field which has divergence 0, then it is called divergence-less. So if del dot v equal to 0, then what would be the flux? V dot ds is 0. There will not be any flux for such vector field, the vector field which is having divergence-less vector field. So divergence-less vector field is also called solenoidal field. Divergence-less vector field is also known as the solenoidal field. Okay, so that's all about the discussion about the integral calculus. So we have started with the integration, the definition of integration. Okay, so the integration is nothing but the summation. So integration is nothing but the summation or the continuous summation, and from which we have moved to the different types of integration: the line integration, surface integration, and as well as the volume integration. Okay, and thereafter we have discussed each of these integration in detail using some examples, the line integral, surface and volume integration, and we have introduced the concept of the conservative nature of vector field, and we have also not shown that this conservative field can be represented in terms of the gradient of some scalar field. That scalar field is called the potential in general. Okay, and we have discussed the different the theorems of the theorems in integral calculus, basically the fundamental theorem of gradient, divergence, and as well as curl. Okay, so fundamental theorem of gradient, and from this fundamental theorem of gradient, we can show that the conservative vector field can be represented in terms of the gradient of some scalar field, and those scalar fields are called the potential in general. So we have discussed one example, that is the case of the electrostatics. The electric field is represented in terms of the electric potential in this particular way. Thereafter, we discussed the fundamental theorem of divergence, then the fundamental theorem of curl, and finally we discussed what is meant by the curlless vector field and the divergence-less vector field. Okay, so that's all about this chapter. So we have completed this chapter. So please watch all these videos carefully, and if you have any doubt, post it in the comment box, or you can pass a message through the WhatsApp group or personal WhatsApp. Okay, so that's all for now, and we'll see with the new topic later. Okay, so thanks for watching all the videos. Bye.